So today we're going to prove Lagrange's theorem. This is a famous and often cited result in group theory. The first person to really investigate this matter was Joseph Lagrange, famous for his many contributions to maths and physics, not least of all his two-volume magnum opus Analytical Mechanics, which consolidated and updated all the work that had been done in the previous century since Newton on classical physics, and updated and broke new ground in the subject. His work predates the dawn of group theory. Indeed, he was one of the central figures in the birth of group theory, but a bit too ahead of his time, unfortunately, to really have the right conceptual tools for this theorem. So here we see the statement of Lagrange's theorem. It says, let G be a finite group and H be a subgroup of G, then the number of elements of H divides the number of elements of G. The number of elements for a group is also called its order, so we could say that the order of H divides the order of G, and that is often denoted with vertical bars around the group. So if you see G with vertical bars around it, that means the order. Okay. So you're going to need to know what a group is, so you're going to need to be familiar with the axioms of group theory. We're also going to use concepts such as subgroups, cosets and equivalence classes. If you've taken an undergraduate abstract algebra course, you should have seen all of this stuff before. As I said, this is a result that belongs to group theory, which is one of the main branches of higher algebra. This isn't the elementary algebra that you learn in high school. This is the abstract algebra that you first typically encounter in a third year university class. Nevertheless, it's an easy proof. It's one of the simplest theorems to prove in group theory, and it's one of the first that the students typically see. As I said, Lagrange himself was working in the days before group theory had really taken flight. So he was simply interested in permutations among roots of equations and things like that, which of course people like Galois would eventually seize upon to break new ground in the study of equations and groups. So I've credited here Lagrange, Gauss and Jordan. They independently and quite apart in years proved different versions of this statement. So Lagrange, he had a simple proof of the symmetric group, although you wouldn't have called it that. Gauss, he proved a more special case to the theorem in 1801, and Jordan in 1861 extended it to any permutation group. So let's get started then. Okay, before we dive into the proof, let's just review some group theory concepts. So a set G together with a binary operation star is defined to be a group, provided the pair G and star satisfy four group axioms. So those four group axioms are as follows. Closure, first of all. So that means that for all A, B and G, we have that A dot B is in G. So we can compose elements of our set G using this binary operation. The composition might be multiplication, for example, and the result has to also fall within G in order for this axiom to be satisfied. So the set is closed under composition of elements under this operation, under this binary operation. So that's the closure axiom. The identity axiom says that for any A in G, so for any element in the set, we also have a special element exists, we'll call it E, and this exists such that if we compose E with any element, we just get that element. So that would be, in this instance, a right identity because it's multiplying on the right. We would also have that E dot A must be A. So this is a left identity. So we want our identity to be a right and a left identity. And whenever you compose any elements with the identity, the rest of the composition is unchanged. You just get back what you started with. Associativity, well, this is the condition that for all A, B, C, so if we pick 3 arbitrary elements from the set G, we want the condition to be that A composed with B and then composed with C is exactly the same as A composed with B composed with C. In other words, the order of composition does not matter to the final result. We can arrange the brackets in any order we like and we'll get the same answer. And finally, the inverse axiom says that for all A in G, for all elements in G, we must have another element A inverse such that A composed with A inverse gives us the identity element. So every element has an inverse element which composes with it to give the identity. And any set which has a binary operation defined on it and satisfies these 4 axioms is a group. Okay, so we covered the idea of the order of a group. So remember that was written like this. So finite groups are those which have a certain number of elements, i.e. n elements. So we could say that the order of G is n, and we denote the order by these spherical bars. Infinite groups also exist, where they have countably many elements or even more. So the order of G could be A left null, or even greater numbers, but we won't go into that. So we're just dealing with finite numbers, finite groups in this video, and Lagrange's theorem only deals with finite groups. So if we start by assuming that we have a group G which has n elements, a subgroup of G would simply be a set. So H is a subgroup of G if and only if H, so H is a set, just like G is a set. H has to be contained in G, properly contained. Well, it could be it could be the set, it could be the same set. If H is contained within G and H is a group under the same binary operator star, the G had defined that. So G star is a group, H with the same star operator is a subgroup, and the way that we write that would be H is contained in G. So there we have the notion of a subgroup. So let's look at the idea of a coset. So we can intuitively think of this by drawing a space to represent a set G, or a group G rather. Of course it has an underlying set, but it also has an operation defined on it. And any two elements, you could think of them as points in this space, and if you compose point A with point B, you'll get point D or whatever, like C. And you won't be able to escape from the space using the elements in the operation. You'll have to remain inside this set. So pick another colour. Yeah, so we could say that within this space G we have a subset H. If H also happens to be a group, then we say that it's a subgroup of G, i.e. if you take two elements in this subgroup and compose them, the answer you get will still be in this subgroup. It will be another element of the subgroup H. And all of these operations we're doing are all with respect to the same binary operator that we started with. Okay, so let's now take an arbitrary element A in. Let's do this in the other colour. Let's take an arbitrary element A in group G, and take an arbitrary H in H. Now if we do A times H, or A composed with H, that will be in a new what's called a left coset of H. So little h was an arbitrary element in this subgroup, A was an arbitrary element in G, and by we now have a new coset we can call AH, and we can then multiply by A again, A squared H, that would be in A squared H, and you can imagine, we can look at the diagram here. So this would be the coset AH and the coset A squared H, etc. So what's really happening is we're partitioning the big group G into smaller, these won't all be subsets, only H is a subgroup. Sorry, they will all be subsets, only H will be a subgroup. But by taking an arbitrary element A, each time we multiply any element in H by A, we'll move into a different coset. So each of these, AH, A squared H, A cubed H, and so on, these are all the left cosets of the subgroup H. and we're almost there. So the proof of Lagrange's theorem is simply to recognise that when we partition G into these various cosets, the number of cosets times the number of elements in H will be the number of elements in G, because all of these are all subsets of G that have the same number of elements. They're all equivalence classes of G. We've discovered that the cosets of H partition G into equivalence classes. Now there will be the subgroup H, the number of elements in that we denote by the vertical bars, remember, so the order of H is the number of elements in this first partition here, but we know that every partition will contain the same number of elements. So there are really, let's say there are n such partitions, so n, the number of partitions times the number of elements in each partition will be equal to the total number of elements in the group. In other words, the number of elements in the subgroup divides the number of elements in the group, and that concludes the proof of Lagrange's theorem.